Okay, so in our last video, we talked about this idea of being able to charge up something, right? So we use the idea of a balloon and thinking about the balloon has the matter it's made out of, and matter has this fundamental trait of nature, these positive and negative charges, and those charges are movable, specifically the electrons, right? So we talked again last time about, if you had some kind of cloth or whatever and you rubbed the balloon, that you could add or subtract charges. Let's pretend that we added electrons to the balloon. Now the balloon's overall negative, right? And so now you have these charges essentially at rest, right? So that term electrostatic, charges at rest. What we're moving on to today is this idea of not just charges at rest, but some other terms and how could maybe charges start moving and doing some cool stuff, okay? So let's imagine instead of a balloon that somehow we had some kind of a container, right? So I'm gonna draw it just as a jar, which is just some abstract idea. But imagine that we could shove electrons in this jar, okay? The more electrons we added to the jar, the greater a desire for those electrons to get out of the jar, because negatives repel negatives, right? Now, imagine we had a lid to hold those electrons in somehow. Every electron that we added to the jar would increase the desire for all of those electrons to fly away from each other. Essentially, what I'm getting at with this idea is the term voltage. Voltage is essentially the push or the desire behind charges to go somewhere else, right? Now, if we think about like go somewhere else, where are they gonna go? It's a jar. If the lid was opened, if they weren't contained, they'd wanna get out, right? But let's add to our idea. Those charges would only wanna get out if the outside of the jar was a less negative place, right? So if we think about normal like air in the room, normal air in the room is going to have negatives and positives around also. So is that going to be a place these electrons can go? Well, yes, because in the jar we've got all these electrons that are all crammed together. If they came out of the jar, they could go from here out into the room. There's a desire for these charges to go to another location. So we would say in a comparison between these two places, there is a voltage. There's a desire to go from one place to another, okay? Now, we see this in nature quite a bit in storms, thunderstorms, right? So as air rises due to heating from the sun, right? We've got this nice scenery here, a tree and some mountains. As hot air rises and takes moisture with it, and then little droplets of water are falling, you have kind of this same sort of rubbing scenario like we had with the balloon, where charges can get moved. And in thunderstorm clouds or thunderheads, you end up having a separation of charge inside the cloud. Now, I'm going to say it's negative at the bottom and positive at the top. That's not always the case, but just for our drawing, that's the idea. Okay, so kind of like the balloon, separation of charge, or kind of like the jar, a bunch of charges in one place and they'd like to go to another place. If the voltage builds up great enough, then you can actually have a discharge of charges from one place to another. So you could have lightning within the cloud. Or this very negative bottom to the cloud could induce a positive charge in the ground. And what I mean by induce, the presence of all these negatives, it's going to push electrons that are in the ground away, and then you have this voltage created, this desire for charges to rebalance, okay? And so then you could also have a lightning strike that shoots more like so, okay? So the term voltage, bringing it back to the physics, the term voltage is referring to the desire for charges to move. I typically use the word push when we think about what does voltage really mean. It's the push behind the charges. How much do they want to go from one place to another? And voltage has the units of joules per coulomb. But we call those volts, okay? Now, the next concept that's important in this idea of not just electrostatic sitting still, but more interesting charges moving, is once this voltage builds up great enough, like we saw in the cloud, and we get charges moving, then we'd have a flow of charges, in this case in the lightning bolt, right? It's a flow of charge. And we would call that a current. So voltage was this desire for charges to move. Current, just like the current of a stream, is the flow of charge. And current would be in the units of coulombs per second. How many coulombs are flowing through a certain location every second. And we call coulombs per second amps. Okay, so if you've heard these terms volts and amps before, hopefully this is starting to come together to make a little bit more sense. All right. Now, we kind of use this just sort of nature concept here. Let's take it to a little more of a kind of a design scenario, so to speak. If we think about some chemistry, there's reactions where electrons are released from the reaction, and there are reactions where electrons are taken in by the reaction. So let's consider a solution with some kind of metal probe in here, okay? And we're going to say that that metal probe has iron in it. Iron is fairly easy to steal electrons from. So it's easy for electrons, sorry, not electrons, it's easy for iron to lose electrons and become positively charged. And then we have kind of these free electrons, like they've got to go somewhere, right? So if we had a solution that was maybe good at taking electrons, and we had a metal that has iron in it in that solution, then we're going to have that solid iron losing electrons and becoming positive iron ions that float around in the solution. Well, what if we put a different reaction near it? In this solution, we're going to say that we have copper ions due to putting some sort of powder, copper powder in there, right? And then we have another metal probe in here, okay? Copper is better at gaining electrons than it is at losing electrons. So when we look at kind of a chemical equation, so to speak, we would say that copper ions are good at gaining electrons and becoming solid copper, okay? So we have a reaction here that is good at losing electrons, a reaction here that's good at gaining electrons. If we connect these two with a material that will allow the flow of electrons, then we will actually get a flow of electrons, right? So if this is the iron side that wants to lose electrons, this is the copper side that wants to gain it, we should see electrons flowing through this conductive material. Now, there's a couple other little things that have to happen to balance the solutions out and keep this working, but you get the idea, switching from kind of what happens in nature to something that we can force. This is the basis of a battery, right? The voltage on this side, in my simple battery here, the voltage comes from the two different chemical equations that are happening, these chemical reactions. That is the push behind the charges. And then the wire here allows for the flow. It allows for current to be present. Right, the flow of charges. Now, the last important term when we think about kind of electric stuff doing cool things is the idea of resistance, okay? So resistance is present in any conductive material, okay? So it's like, how do you draw that on here? I kind of already did, right? In my battery drawing, the wire itself has resistance. It resists the flow of charge. Let's write that in here. Resists the flow of charges. Now, if you think about why, there's lots of different kind of models you can imagine. If we imagine current as the flow of charge, charges are actually flowing through this wire. They're really jumping from like one atom to another on their way through here, and that takes time. They have to, like, those charges bump into other things, and it's kind of like, imagine a crowded hallway and someone's trying to like go through that crowd. There's just going to be resistance there. In my lightning example over here, the charges that are building up in the cloud and in the ground, those charges have to go through the air. The air is a terrible conductor. So you have to build up huge voltage to overcome that resistance to get things through. Okay, one last concept here with units, because we talked about volts being joules per coulomb, we talked about current being coulombs per second. Resistance, like, what are the units of resistance? This is kind of a weird one. Resistance is ohms. And then you're like, well, what's an ohm, right? How does that connect? Well, they're called ohm because the relationship between all these things was defined by a scientist with the last name Ohm, who developed Ohm's law. And Ohm's law says that the current flowing through a situation will be equal to the voltage present divided by the resistance. Now, what's kind of cool about this is that the units for resistance were really kind of established by Ohm. There wasn't a pre-existing unit for resistance, so we don't need a constant here to adjust units. It's just like R is resistance and sort of, I guess, a constant all mixed together, right? So we just say resistance is ohms. Now, ohms can have a fundamental unit if you look at what they need to be in order to cancel and give you what you want, okay? But what's more important to think about here is, in a situation where current can flow because of voltage, if we imagine increasing voltage, if voltage goes up to a bigger value, what does that do to something else in this equation? Well, if resistance stays the same, right, like it's a wire or it's air, then that means that the current will get bigger to keep this relationship the same. And you could say kind of something similar if you had a situation where voltage and resistance are causing current. What if resistance changed? In that case, you have an inverse relationship. If resistance gets bigger for some reason, then that means the current has to shrink to a smaller value to keep these things equal. All right, lots of cool stuff to think about. Voltage, current, and resistance, the three main things in any kind of circuit, really, but in any kind of situation where you've got charges that can move, you'll have those three things, and Ohm's law defines the relationship between them.